Okay, I disconnected the phone, so there won't be any more interruptions, but that means that every one of these things gets to be little pieces. So let me see if I can get back on track here. So we are doing the eigenvector derivatives, we get to this equation, this is a linear system of equations, this is what we're looking for, this is the coefficient matrix, and it's a vector. But we face this situation. The matrix Cj is rank deficient, and we know that the vector phi j times it is 0. Now, what does that eventually mean? Well, what it means is this. What it means is, imagine that I postulate that phi 0 j prime, okay, is something such that zj times v0j prime is in fact equal to bj, okay? Don't worry about right now, how did I get this? That doesn't matter. The point is, let's just say that I know that if I put that vector here, I get the right answer, I get the right side. But since we know that phi j, that zj times phi j is 0, because this is rank deficient and this is in the null space, then it turns out that this will also be true, right? Because if this is that and this is 0, then this is also true. So the question is, how should we select the value of n? I repeat, I have not at this point stated how I got this term here. I'm just saying, take my word that I found a way to find something here that works, okay? What I'm saying is that when I find something that works, anything that works plus any number of times the eigenvector phi j will also work. And the question then is, how do we select the value of n? In the literature, there is a lot of discussion about how this n has to be selected, and as far as I can tell, sometimes significant confusion. What I want to, well, maybe, I don't know if I should do it right this second or not. Maybe not. Maybe I won't do it right this second. You know why? Because I believe that without the background from the singular value decomposition, it might not be really very clear. So what I am going to do is to actually put this thing in writing and upload it to the website so that you know, you can see it carefully, and I can also think about it carefully and have it to you after the background of the singular value decomposition. But the point is this: it can be shown, at least I have shown, that if phi 0j prime is the solution of minimum norm, then n is 0. Okay? Now, what we mean by the solution of minimum norm is, of all the possible vectors that you could multiply times zj that give vj, there is one solution for which the norm of that vector is the smallest. That solution is what we call the pseudo-inverse solution. So phi 0j prime is simply zj, and this plus sign means pseudo-inversion. The pseudo-inversion is connected with the singular value decomposition. At this point, as I say, I'm just going to leave it like that and this. And so, since n is equal to 0, we conclude that, or I'm arguing, I'm contending that it's equal to 0, I am concluding that phi j prime is exactly phi 0 j prime. Okay? And then we complete our equations by gathering on this side the following result. Phi j prime is equal to z pseudo inverse j times bj. In MATLAB, the command pseudo inverse is just PINV, right? So this would be something like this, PINV of CJ, right? If you were in the MATLAB command. To have the meaning, theoretically, we will have to do the singular value decomposition in more detail. Now, so far then, we have that the derivative of the eigenvalue with respect to the parameter is the left side eigenvector transpose times the derivative of the matrix times the right side eigenvector, and the derivative of the eigenvector is equal to the pseudo inverse of the matrix Zj times the vector Bj, where the matrix Zj is equal to, what was it, the identity times, A minus the identity matrix times lambda j, and the vector Bj was, what was it, was the identity times lambda j prime minus a prime multiplied times phi j, right? So these are all the equations that are necessary to take the first derivative of an eigenvalue that is non-repeated, the first derivative of the eigenvector of that. Now, we can also do the following, and it's useful in some applications. If we take another derivative here, we have that the second derivative of the eigenvalue, using the change rule, again, is equal to phi j transpose phi prime j transpose times a prime times phi j plus cj transpose times a double prime times phi j plus cj transpose times a prime times phi j prime, right? Now, in most instances, or in many instances, the matrix A is linearly dependent on the parameter, and so A double prime is 0. And in that case, the second derivative of the eigenvalue is equal to these terms here, right? And wait a minute, did I do something wrong here? No, it's correct. So we have phi j transpose prime times a prime times phi j plus phi j transpose times a prime times phi j prime. Okay. Let me think. I just want to double check something here. Derivative. So phi j transpose prime times a prime. Okay, yeah, we can also write this for the sake of symmetry, like this. Phi cj transpose plus the derivative, right, times a prime times phi j plus phi j prime, which is kind of an elegant expression, right? If we compare these two, we can see that the first derivative is the left side transpose A prime, the right side. The second derivative is the left side transpose plus the derivative of the left side transpose times A prime times the right side times plus the derivative of the right side. Okay? Now, you might wonder, why would I want to know the second derivative of the eigenvalue, for example? Well, let's see, I can erase this part and still leave it there. Imagine that you plot, or consider the case where you plot the eigenvalue here, and let's say the parameter here. So when the parameter hasn't changed, the eigenvalue is this much. As the parameter changes, you could have a situation perhaps like this. So this is how much the parameter changed, right? Or you could have a situation like this. Right? The change same of parameter. Now, this slope here, that slope is the derivative of the parameter with respect to theta, right? So what this means, maybe I went a little too far here to make my point. But what I mean is that if I want to know how much is my eigenvalue going to change due to this much change in the parameter, the linear estimate is reasonable, still significant error there. So let me just show it like this. Okay, the estimate of the change based on the linear estimate is reasonable on this line, but quite wrong on this other line for that delta theta. And why is that the case? Because this case corresponds to a second derivative which is small. That is, there's not that much curvature here. And this one is, of course I'm talking about at this point, right? But here is the second derivative which is large. So if I am trying to find out under what conditions I can use a linear approximation of where the eigenvalue is going to go as I get damage, then this formula is going to allow me, when I'm working with a model, to know whether linear approximations are reasonable or not, or more than that, it allows me to make estimates with the second order theory. For example, I could say that the eigenvalue as a function of theta is approximately equal to the eigenvalue originally, when there is no change in the parameter or no damage, plus the derivative of the parameter of the eigenvalue multiplied times the change in the parameter, right? That would be this part, plus in a Taylor series we would have the second derivative of the parameter times delta theta squared divided by 2. That would be in a Taylor series form, right? For example. So I will conclude the lecture by looking at the one last item, which is, what are we missing in order to evaluate this? Do we know how to get the derivative of the right side eigenvectors? Yes. Do we know how to get the derivative of the left side eigenvectors? No. Okay? So we need a procedure to be able to calculate the derivative of the left side eigenvectors. Okay? So with that, I will conclude and let me see, the way that we are going to do the derivative of the left side eigenvectors is as follows. Imagine that you get a small change in the parameter, then you would say that this would be the eigenvector updated, right? This would be the updated eigenvector. Now, if we do the same thing with the left side, we would say that the left side updated is equal to, is equal to the left side without updating plus the derivative of the left side times epsilon. Now, one of the questions I was asking class is, what is epsilon? Okay? And epsilon is just a small parameter, anything. Eventually we will say it doesn't matter. This is a infinitesimal change, right? This is where the eigenvector is going, this is where the left side eigenvector is going. Now, we want the transpose of the left side eigenvector times the right side eigenvector to be 1. So we need this to be preserved when we multiply these two things, right? So let's multiply them. So if I take this transpose, I get phi j transpose plus phi j prime transpose times epsilon, right? Because the epsilon is a scalar. And then we're going to multiply that times this, which is phi j plus phi j prime times epsilon. And we want that to be a 1, right? So this gives us phi j transpose times phi j plus psi j prime transpose times times phi j times epsilon, right? This times this plus this times this. And now we want to do the second one, so plus phi j transpose phi j prime times epsilon, this one times this one, plus phi j prime transpose times phi j prime times epsilon squared equal to 1, right? So that means then that since this right here is a 1, and that's a 1, and this has an epsilon squared, which we can approximate as 0, then we get that phi j prime transpose times phi j plus phi j transpose times phi j prime times epsilon is equal to 0, right? Okay, where is the thing? Now, that is equal to 0. And from that equation, the reason why I was hesitating, I just now recognize it, because in the class I did something slightly different. This now concludes, it's not incorrect, but we will see that it is problematic, times phi j is equal to minus phi j transpose times phi j prime, right? Now, what happens with that right here is that you can see the following. Do you know the left side eigenvector? Yes. Do you know the right side eigenvector derivative? Yes. Is this a number? Yes. can you with this calculate the left side? No, because what you get is something like this. Let's say there were 4 numbers in this vector. So we want to get these 4 numbers, they are multiplied times A, B, C, D, right? And they are equal to some number P1, which was this part. So I really cannot solve for this eigenvector by doing that, right? Now, if I do all of them, then I can. Let me see, in class I did it differently, but let's say that we had, let me see if I can show it here quickly like this. Assume that I did this for the first eigenvector, so this would become the left 1 transpose. If I did it for the second one, this would be V2 transpose. If I did it for the third one and for the fourth one, I'm using just 4 to illustrate the point. So I would have something like this. This matrix would then be multiplied times the matrix. I always put the matrix on top so I can see the order. It would be multiplied then by phi1, phi2, phi3, and phi4, right? And it would yield the matrix of the left side eigenvectors transpose. These ones, of course, are the derivatives. And so this would yield the left side eigenvectors transpose, phi1 transposed, 2 transposed, 3 transposed, 4 transposed, multiplied times the matrix phi j primes. Okay? So from this perspective, the point is that if we write this system of equations for all the modes, then this becomes simply all of the left side eigenvectors, all of the derivatives, all of the right side equals minus all of the left sides transpose and the matrix of all the derivatives of the right side. Okay? Now, in that case, now we have a square system. And from